So in this chapter we're going to look at how charged particles are affected by electric forces and magnetic forces, or collectively electromagnetic forces as it's often referred to, because we'll find out they're just both aspects of the same thing. So we'll start by looking at electric fields. So first of all, let's just define what an electric field is. And it's a space. Fields in physics mean spaces. An electric field is a space around a charged object where another charged object will experience a force. So, for example, the charged objects, it might be around about charged particle, it might be between charged metal plates. Okay, and we'll look at that in the next part. So we'll look at those kind of standard diagrams. So what does the electric field look like around, say, just a single negative particle? If we represent that as our single negative particle, the definition of electric field, the direction of it is chosen to be the direction a positive charge would experience a force in. And so negative charges would just be the opposite. So a positive charge would be attracted towards a negative charge. So if I had a wee positive charge somewhere in this field, then it would go directly towards, and you need to draw these using rulers. It's hard for me in an iPad, it is possible, but it takes too long. And what we have, these are called radial fields, right? Because each of these is like a radius of a circle. And what we find is that they are far apart when you're further away from the charge, and closer together the closer you get to the charge. And that represents the strength of the field. The closer together the field lines, the stronger a field will be. We need to know, be able to draw or to recognise as well the similar pattern for a positive charge. So if your object setting up the field is positive, then any positive charges in that field would be repelled as opposed to attracted. And a couple more patterns, just the same as the ones you met in that 5. What happens if we put a pair of these charges close by each other? Well, basically we take these two patterns and bend them round each other. So if you look at the right hand side of the negative and the left hand side of the positive, well, they're both just coming straight, so that's a nice easy one. It is a straight line going in that direction. But what happens, the other ones kind of get bent round a wee bit. So the one that comes out here for the positive will bend round that way. That one will bend round that way. Top one would probably bend a wee bit that way. We're just kind of bending round. And round the far side you're not likely to be significantly affected. And the very last one, which I'm going to use a ruler for. So the last one is two parallel plates. And we attach one end to the positive end of a battery, one to the negative. So these lines represent connections. And what we find is that we get what's called a uniform field. So we get a series of straight lines. So basically, if you look at that diagram to the left with the single positive and negative charge, is we get a whole series of them. So that straight line in between the two is replicated all the way up and down this plate. So basically you've got matching pairs of negative and positive charges. Now you do have to be quite careful drawing these. So let's say definitely using a ruler and trying to keep them all fairly evenly spaced as well. And strictly speaking as well, you do get some what are called edge effects, which means that around the edges it kind of curves a wee bit. So if this was our negative plate here, and that was our positive plate, then let's get our direction specified. But the edge effects, as I mentioned, would be at the top and bottom of the one above. I don't think they should be asking that, but I think there was one question that came up somewhere where they specified those edge effects, so I doubt they would ask in the actual higher. So they're the field patterns you should know either to recognise or to draw. Anyways, the final one there is the most useful one when you have a uniform field, because then the forces are constant and that makes the equations a lot more straightforward. So that's the one that we'll concentrate mostly on in higher. And basically what the idea is, if you move a charge within that field, then either if you're moving against the field, you're going to have to do work, you're going to have to put energy in, or if the charge is moving itself, then the field does work for you. Right? So if you let a charge go so that it accelerates on its own, then the field will do the work for you. So in theory, we could do this, analyse it in terms of using forces and working at accelerations, but we tend to analyse it in terms of energy, so we use that idea of work done. And so we've got a few simple learning outcomes then. So first of all, work is done. So just to emphasise that point, when a charge is moved in an electric field. Is moved or moves. And we define from that the idea of potential difference. So if we go back to those parallel plates, I said we made one plate negative and one positive by applying them to a battery. And remember, we stressed this idea of potential difference rather than voltage in that 5. Basically, this stresses that idea. A bit like moving up and down a hill. You can either put energy in to move something up a hill, or you can let it roll down the hill to get the energy back out. We can do the same idea in an electric field. And we define then potential difference. So we'll get another state of that one here. So the definition of potential difference is the work done per unit of charge, or in moving 1 unit of charge, 1 coulomb of charge. We met those units back in that 5, between 2 points. Now if you struggle to remember that, you have a formula, okay, that will come up to the next couple of learning outcomes. But basically, potential difference V, you can rearrange the formula as W divided by Q, the work done per unit charge. Right, so remember, you can use formulas. Linked to this, we also use it to define the unit. All right, so a potential difference of 1 volt. Means 1 joule of work is done in moving 1 coulomb of charge. And let's say there's an equation to go with that, and we'll look at a worked example. So our equation, I don't know why they write it with the capital W, actually, because I would prefer it as EW, which is what we used for work done before. But we'll just bundle them both together to emphasise. And then over the page, we'll look at a worked example of that. So it's a fairly straightforward worked example. We are given that the charge is 3 microcoulombs, which will translate 3 times 10 to the minus 6 coulombs. The potential difference is 10 volts, and therefore the work done. That's what we're being asked. Electrical potential energy gained is how it's phrased, but that means the change in energy. And remember, work done is just a change in energy. Okay, so it's not huge amounts of energy involved. The charge is now released. State the energy change. So we've given it electrical potential energy. Okay, and that would then convert back, if you now released it, into kinetic energy. How much kinetic energy will be gained on reaching the negative plate? Oops, well, it's just going to be the same. The work done that you put into the system and dragging it towards the positive plate is going to be converted back into the kinetic energy. So the kinetic energy will also be 3 times 10 to the minus 5 joules. 7 is a wee bit of a repeat of number 1, but in an electric field, a charged particle experiences a force, but I think the only bit it adds is the direction of the force, although we've mentioned it, we've not actually written it down. So the convention is that field lines show the direction a positive charge would experience a forcing. And what this means then, we can use this to explain how conductors work. So, in a conductor, the free electrons, i.e. electrons which are not tightly bound to atoms, will drift towards the positive end of a power supply. So basically, a battery or any type of power supply sets up an electric field throughout the conductor so that the free electrons drift towards that positive end. So the electrons are already there in the conductor. That's what makes it a good conductor, the fact that its electrons are not tightly bound. Then when you apply the electric field, that starts them moving. So number 9 we'll do a worked example for as well. So it's about using conservation of energy to calculate the speed of a charged particle. This question splits up into 2 bits. You work out the kinetic energy, you use that to work out the speed. Sometimes you won't get that as two separate bits, you'll just be asked to speed, so you could be asked to do this all in one step. So part A. So we're given the voltage is 200 volts, given the charge. Now notice we don't actually put the sign of the charge in, because we'll deal with that if the question requires us to think about the direction in the diagram. So it's the magnitude of the charge really here that matters. And we're also given the mass. And the first part, we've been asked the kinetic energy. Now we don't have the V to get the half mv squared, that's what we're going to be working out next. But what we can do is use the idea of conservation of energy to say, well, that is the work done. Okay, the work done on the electron is the change in energy, and it's gaining kinetic energy. So the kinetic energy gained is the work done. And then we can substitute in the values we've got. To get the kinetic energy. And then we can use that kinetic energy as to get the velocity. So we can now say Ek equals a half mv squared. Fill in our value of Ek. Fill in our mass. And don't forget the squared on your V. And then rearranging that, give you V is 8.4 times 10 to the 6. Remember, if you get bigger than the speed of light there, you've made a mistake. Okay, it's a useful check. And the only other thing I would say is that you sometimes see these two formulas all combined into one. So you'll see that written sometimes QV equals a half mv squared, but it just comes from the two separate formulas. And in number 10, we've got a wee bit about magnetic fields. We don't do a great amount of detail, we don't do any formulas to do with magnetic fields, but I'll give you the definition and then we'll talk about how we use it. So a magnetic field, and let's say we're not doing as much detail, so we're not necessarily talking about what produces a magnetic field, but it's a space where a moving charge experiences a force. But that's the difference between the electrostatic, or just electric force, and magnetic force. So they're both closely linked. But magnetic fields apply to moving charges, electric or electrostatic fields apply to stationary charges. But what we need to do is we concentrate on using magnetic fields to change direction. So the learning outcome says describe the direction of the force on a charged particle moving in the magnetic field. And basically we use what's called the right hand rule for this. So if you can imagine the first three fingers, I know you've got diagrams of this in your notes. So if you take your thumb and your first finger and your second finger, and hold them up like that, then the thumb represents the thrust or the force. The first finger represents the field, and the second finger, the EC part of second, represents the electron current, i.e. the movement of a negative charge. So using that rule, you can work out in any situation, if you've got an electron moving, line it up with the field. Now notice all of these are at right angles to each other. If we won't give you questions where they're not, but if it's not at right angles, if it's going along a field, then basically, if it's going along a field line, then there's no deflection due to a magnetic field. So we'll all set it up so it's going at right angles, and then you'll get a force applying at right angles again to that. So this is the right hand rule. And then 11 is describing the basic principles of a particle accelerator. So really what we've got to get, there's two important parts, the two types of fields that we've been studying and the end result of that. So we're looking at acceleration, deflection and collision. Okay, so the most basic accelerators were all just in a straight line. Right, so we use electric fields to accelerate charged particles. So it could be electrons, could be protons, can be actual whole atoms if you want, and so on. And let's say, to start with, we just had linear accelerators, so you just had these fields set up in a straight line to accelerate them. But that's kind of wasteful, because once you reach the end of that, that's all. You've got to have your target at the end, have your collision. Somebody came up with the idea, well, if we could deflect it back round, we could use the same accelerator again to accelerate it even more, and so on. So we use magnetic fields to deflect the particles in a circle, so they come back round to the accelerating point. And lastly, when moving fast enough, can collide with a stationary target or other moving charges. So head-on collisions are good because they give you maximum energy. If you've both got the two objects moving directly towards each other, it'll give you the maximum energy of collision. And I'll just show you a rough schematic of that sort of idea over the page. So you would have deflection, acceleration, deflection, and then maybe a space where you could have a collision if once you're going fast enough. Deflection, another space. You could have acceleration in multiple parts. So I'll put B, because historically that's a letter used for magnetic fields. And they're deflecting, and we could have A for accelerators, and let's say we can have multiple accelerators if you want. A is the electric field, and in C, either just let it through if it's not going fast enough. C are points where you can put in experiments and allow the collision to take place.